As we begin section 1.3, we will start discussing complex numbers, or you may have heard of imaginary numbers. Now, they're not pretend, they're not fake. It simply means that we have additional numbers that we can use in addition to what's already in the set of real numbers. So let's define what an imaginary number is. And it's simply this: if you had worked in high school algebra and you had tried to simplify something that had a value that was negative underneath a radical, for example, the square root of negative 25. What you would have been told is at that point you would say no real solution. And that's true. There is not a real number solution for that number, because a square root is actually asking you what number can you multiply times itself and get back the value underneath the radical. If that was a positive 25, then you would look at that and say that my answer would be 5, because 5 times 5 is 25. In this case, it's a negative 25, and we cannot multiply a number times itself and get a negative number back using real numbers. It can't happen. So because of some uses that we're going to find in working with electricity, in certain fields in engineering, there's a need for being able to simplify or solve something that has a negative underneath a radical. And so that's where the imaginary unit comes in, or the imaginary number I. It simply is a tool that allows us to deal with that negative under the radical. So if you look at this definition, I is defined to be the square root of negative 1. I equals square root of negative 1. Now, because in algebra we can do the same thing to each side of an equation and not affect the validity of the equation. If you square both sides, that means also, by definition, that I squared would be equal to negative 1. Those are very helpful definitions to know. Now, these imaginary parts are found in what we call complex numbers. The real number system is a subset, or it is included within the group of complex numbers. And look at our definition for complex numbers. If you come to the box below, it says if A and B are real numbers, and any number that would be in the form A plus BI. So in other words, I can have a real number part and I can have an imaginary number part, and they would be added together. When that happens, we have a complex number. So in the complex number A plus BI, A is the real number part, and the B is the imaginary part, or the coefficient of the imaginary part. Now, this, we need to make sure we kind of get a handle on these number sets. If you look at the next paragraph, all real numbers are a subset of the complex numbers. If we look at our definition for a complex number, that means B was equal to 0. That's why I didn't have the imaginary part, because B was equal to 0. So real numbers would be a subset. The difference between a non-real complex number and a pure imaginary number is the value of A. If A equals 0, then that means the only part that I would have is the imaginary part. No real part exists, and that would be a pure imaginary number. But if both A and B do not equal 0, then the number is non-real complex. It's a complex number that has to include the imaginary part. Remember that a number may be classified in more than one set of numbers. So let's do a few examples to be sure we can classify these correctly. If I look at the first one, the number is negative 15. So here are my choices. Is that a real number? I would hope you would agree that it is. It's real. Would it be non-real complex? Now, obviously, if you think about it, can something be real and non-real at the same time? Those are mutually exclusive. They cannot be both. Is it a complex number? Would this meet the definition for a complex number? I hope you realize the answer is yes. It's a complex number where the b was equal to 0. And pure imaginary means that it has to have the I in it. That's the only thing I see is the imaginary part. Obviously, that is not the case here. So I have two answers on A. Now, if I look at B and I run through my list, the number 8i, can it be real? If it's real, then it's not imaginary, so it can't be real because I see the I. But is it non-real complex? The answer is yes. It's a complex number that is not just a real number. Is it complex? Well, if it's non-real complex, that also means that it must be complex. Remember, if the real numbers are a subset of the complex numbers, wouldn't complex need to be in the list for every number that we're going to see? The answer is yes. I hope you see that. Is this one pure imaginary? Is the only thing you see the imaginary part? And the answer is yes. We get all three on this one. We'll never have all four at the same time because it can't be real and non-real complex at the same time. Now, if you look at the last one, 5 plus 4i, would that be a real number? If I see an I in it, it can't be a real number, so it's not that. Is it non-real complex? And the answer is yes. Because I do see the imaginary part that makes it non-real complex. Is it complex? I hope you remember that yes, all of these will have to be complex, but is it pure imaginary? If it's pure imaginary, then I don't have a plain real number part in addition to the imaginary part. And this one has both parts. The A is not 0, so it is not pure imaginary. Hopefully those classifications make sense now. If we look at the last part of this page of notes, and remember when you get to the bottom you can arrow over to the next slide, we will practice how to simplify these radicals that have negatives underneath and turn them into complex numbers. Now, on something like A, where the value is square root of negative 81, remember, I can rewrite this as the square root of negative 1 times the square root of 81. As long as I have something under the radical, I can rewrite it as a product that would be equivalent to whatever that original number is under the radical. Negative 1 times 81 is the same as negative 81. The benefit of writing it this way is, by definition, I know what the square root of negative 1 is. It's I. And as it turns out, the square root of 81 is a perfect square. That gives me the number 9. If I multiply I times 9, I will get 9i. And that is how the square root of negative 81 simplifies. So as long as I've got a perfect square, that's going to be very easy to simplify. If I see the negative sign under the radical, what I usually tell students is don't forget to take your I out, okay? If you think of it as the square root of negative 1, then you know that the square root of negative 1 is I, and that's how you can simplify. Now when you move to B, we have the same issue, the square root of negative 55. If I think of it as the square root of negative 1 times the square root of 55, the problem is 55 is not a perfect square. So if I have a number under the radical and it's not a perfect square, I need to see if it could simplify. And in order to do that, I would encourage you to consider using prime factorization. You can make a factor tree, or you can do the backwards division or the ladder method for factorization. Basically, prime factorization means I want to write this as a product of numbers where I'm using only prime numbers as products. If you don't remember, a prime number by definition is a number divisible only by itself and 1. So if I look at 55, I know that 1 and 55 are factors. The only other factors I have are 5 and 11. 5 times 11 is 55, and both 5 and 11 are prime. So the fact that I didn't get a pair of numbers I could multiply together that would be a factor of 55 tells me that it will not simplify any further, and this simply becomes I times the square root of 55. Now, notice on A, we put the 9 in front of the I. That would be in standard form, because if you remember, standard form for a complex number was A plus BI. The only reason I'm putting the I in front of the radical on B is simply because there's a radical involved. If I were to put the I at the end, it might accidentally appear as if it were under the radical, and that could be confusing. So in the case of having a radical, it is okay to put the I in front. In fact, it's preferred simply because it reduces the possibility for confusion. One more example of simplifying these complex numbers. I have the square root of negative 98. Now on this one, I know I could think of it as the square root of negative 1 times the square root of 98. And hopefully I recognize 98 is not a perfect square, but it could be simplified. And that's what we have to make sure we do, is simplify radicals when possible. So let me explain to you this prime factorization process. We'll use this as an example. Remember, prime numbers are divisible only by itself and 1. So the smallest prime number is not the number 1. It really doesn't meet the definition. Divisible only by itself and 1, that's the same number when we're talking about 1. So the smallest prime number is 2, and it is the only even number that is prime. After 2, we would have 3, and then 5, and then 7. Now don't say 9, because 9 is also divisible by 3, so we don't want to use 9, it's not prime, but 11, 13, 17, and so on. Now, typically 2, 3, 5, 7, that's going to cover most of our needs if we remember those. And I will tell you, as long as the number that you're trying to simplify is even, divide 2 as long as it stays even. That's a great way to start because it's easy to divide numbers by 2. So if I divide 2 into 98, it goes 49 times. Now at this point that is not even any longer, but hopefully I'm going to recognize something that divides into 49 that's prime, and I do. It's the number 7. 7 times 7 gives me 49. Now, I have this factored into prime factors. 2 times 7 times 7 gives me 98. What I'm looking for is to see if I have a pair of numbers. Remember, a square root says what can you multiply times itself? So if I find a pair, I'm going to circle that up, and that means that out of what I circled, I can take one of those 7s, and it goes outside the radical. You can think of it this way. 7 times 7 is 49. What's the square root of 49? It's 7. So the square root of 98, a 7 will come outside to join the I that I know is already there because of that square root of negative 1. And then any value I didn't circle when I did the prime factorization, in this case the 2, stays underneath the radical. So when I simplify the square root of negative 98, I have 7i times the square root of 2. Let's move to the next slide. Now we'll talk a little bit about operations on complex numbers. We need to remember, if we needed to multiply or divide with radicals that have complex numbers involved, do not forget to use the definition I equals square root of negative 1 before using any of the other rules for radicals. If I don't take the I out first, I will be likely to make a mistake. So let's look at a couple of these examples quickly. If I were to multiply the square root of negative 21 times the square root of negative 21, one way you could think about it is, because I see that negative, remember to take your I out. So I'd have I times the square root of 21 times I times the square root of 21. I've got to take the I out of each of them. Now, because I'm multiplying, I can use the commutative property. In other words, I could switch the order of things being multiplied. And if I multiply the I times I, that would give me I squared. And then I would have the square root of 21 times the square root of 21, which is the square root of 21 squared. So all I'm doing is reorganizing the order of my multiplication from the first step to this one. But now I can do some evaluating. By definition, what did we discover that I squared is equal to? Negative 1. And if I were to square a square root, what happens? Well, square means multiply it times itself. Square root means what can you multiply times itself? A square will cancel out a square root. So that tells me that the square root of 21, when I square it, will just be 21. And negative 1 times 21 is a negative 21. Now, there are other ways you could think about doing the simplification, but if you've done it correctly, you would still get this answer, negative 21. Now, when you move over to B, again, don't forget to take your I out, and you would have I square root of 5 times I square root of 30. And at this point, you have some choices about how to simplify from here. If you want to do the prime factorization, then remember our I times I is I squared, and if I multiply the square root of 5 times the square root of 30, I'm simply multiplying 5 times 30, and that would give me the square root of 150. Now if I check, that is not a perfect square. If I try to do that in the calculator, I see decimals, so it tells me it's not a perfect square, but I can simplify that using prime factorization. Now notice 150 is even, so I know 2 will go into 150 75 times. At this point it's not even anymore, but I can divide 3 into 75 and it goes 25 times, and that will give me a 5 times 5. Now when I check for pairs, I see 1. I have a pair of 5s, and that means that will come outside the radical. Whatever I haven't circled up stays behind and multiplies back together. So the I squared turns into negative 1 times, when I simplify the square root of 150, 5 comes to the outside because that's what I circled. On the square root of 2 times 3 gives me 6, so that's negative 5 times the square root of 6. And that would be my answer there. Now when I'm dividing, again, pull your I out first. Be very careful as you do it though. And notice in the case of C, if I pull the I out, I would have I times the square root of 42 divided by I times the square root of 3 on the bottom. And this time, because there's an I on top and an I on bottom, I have a common factor there. That's going to cancel. This will not have an I in the answer. It will not have a negative in the answer. And then for simplifying radicals, since 3 divides into 42 evenly, you could think of this as the square root of the fraction, 42 over 3, which would give me the square root of 14. On D, I notice that in the numerator I have an I because it was the square root of negative 63. But notice carefully there is not a negative in the bottom, so I do not have an I that comes out. This one is going to have an I in the answer. But I also notice 21 divides into 63 evenly, so if I rewrote it as the square root of the single fraction, 63 divided by 21, that would give me I times the square root of 3. Okay, one of the main reasons that we are working with these is because as we move into the next unit, we're going to be working with quadratic equations, and we're going to have some radicals that need to be simplified, and we're going to have to be able to reduce down complex fractions. So in order to do that, let's look at this, and I'm going to give you some step-by-step instructions on how to simplify when you have what looks like a little bit of a complicated fraction. And within the fraction, you see a radical. So the very first thing we want to do is to simplify the radical, if possible. So when I look at this particular problem, I see that the radical is the square root of negative 75. So let's come over here, and if I simplify the square root of negative 75, I can think of that as I square root of 75. Now, I need to do prime factorization on the square root of 75 to see if that cleans up. If you scroll back, though, we really have the work already done for us back here. Notice when we simplified the square root of 150, we got to the point where 75 showed up. 3 times 5 times 5 is the square root, is the factorization for 75. So if we want to take the square root of 75, then we have that 5 that will come outside with the I and the 3 that's going to stay behind. So the square root of negative 75 becomes 5I square root of 3 because of this simplification up here. Okay? 5 times 5 times 3 was the factorization we had for 75. Now, once we have the radical simplified, let's go back and put it in place in this equation. So we have 15 minus 5I square root of 3, and all of that is over 5. Now, in order to reduce this expression down, we want to look for any common factors that might exist on all terms that are outside the radical. Sometimes they may not have a common factor, but if there is a common factor, you will want to reduce down. Now be very careful. Once the radical is simplified, leave the number under the radical alone. I cannot touch that square root of 3. I'm done with it. But remember, we want to put our answer in standard form, which is a plus bi. In other words, we need a real part plus an imaginary part. So what we want to do is rewrite this one big fraction as two separate fractions. Remember, for it to have been put together, it had to have a common denominator. I can go and pull it back apart into two fractions if I write it as 15 over 5 minus 5I square root of 3 over 5. And now when I reduce down, 5 would go into 15 3 times. It won't always reduce to be a whole number, but this one did. And then my imaginary part, I have a 5 on bottom and a 5 in the numerator. That's going to reduce down to be I square root of 3, and that gives me 3 minus I square root of 3 when I simplify. Let's move to the last page. We'll look just a moment at adding and subtracting complex numbers. We probably will not have a lot of need for this, although, again, if you work with, say, electricity, this could be a helpful thing to see. I include it mainly because it's just good practice in combining like terms. And all it says is that if we want to add or subtract complex numbers, then we would add or subtract the real parts. In other words, add a real to a real And then you would add or subtract the imaginary parts. So real numbers get added to real numbers, imaginary numbers get added to imaginary numbers. Now the thing you have to be careful about is pay close attention to the sign that is between the two complex numbers. As long as it's addition, you will probably be fine. Subtraction means you've got to think a little harder. You'll need to think of it as adding the opposite to make sure you get the signs correct. But if we look at A, if I check my real parts, I have a 4 and I have a -5, and because there's a plus sign between them, I'm just adding them together. 4 plus -5 gives me a -1. And remember, it's supposed to be in standard form, A plus BI, so I need to make sure this real part comes first. Now we'll combine the imaginary parts. I have a -5i and a +8i, and I need to add those together. -5 plus +8 gives me +3i. Now when we look at the last example, because there's a subtraction sign in front of that second complex number, I would encourage you to rewrite your problem as adding the opposite, or think of it as multiplying everything in that parentheses by a -1. And that would mean that I would have plus, and then -1 times 5 is a -5. And -1 times -3i would be a +3i. In other words, I'm adding the opposite. The original complex number was a +5 and a -3i, but it was being subtracted. When I change it to addition, these have opposite signs. And now I'm back to where I was on A. I simply put together the real parts, which gives me -15. When I add the imaginary parts, 7i plus 3i gives me a +10i.